So I'm going to be talking about a thing I call stream function, and I'll talk about the concepts and the definitions, work through some examples and to show you how it works, and then talk about some applications of the approach. I'd like to make a few acknowledgements to start with, because this has been going on for a long time now. So it started off with in the Centre for Catchment, Research Centre for Catchment Hydrology in Canberra. Some very strong support from Joe Ritchie and Bruno Basso over the years, and particularly for Bruno Basso, who funded development of some of the software, and also some contributions from Mike Hutchinson from a conceptual point of view as well. So we know that contour lines and slope lines form a curvilinear mesh across the landscape, and the lines cross at right angles. And we know that contour lines are lines of constant elevation. They show convergence and divergence, and the spacing of the lines shows the slope steepness. What about the slope lines? Do they have a constant value of what? And it turns out that you can actually assign a useful constant value to each slope line, which is a thing I call the stream function. So each slope line has its own unique stream function value. The stream function is defined in a way so that the area between slope lines equals the change in stream function between those lines. And the spacing between the slope stream function lines essentially shows information about convergence and divergence. Now, once you've created this stream function map, which I denote using psi, stream function and elevation actually form a flow-oriented coordinate system. So here's a simple diagram of two slope lines and the stream tube between the two slope lines. And the idea here is that each of those lines has its own value. The difference in value across those two lines is equal to the area between them. And we can divide that by a contour line into the contributing area and dispersal area. So anywhere on that stream tube, we have a constant area of the tube, but the contributing and dispersal areas vary depending on where you put that contour line. So it's useful to have a few definitions about terms to keep things clear. So a slope line is just any line that follows the steepest descent at right angles to a contour line. There are some special lines in the landscape. I use the words course line and divide lines to denote the lines going down from a saddle for the course lines and up from a saddle to a peak, which are the divide lines. And then there are also valley lines and ridge lines, which seem similar. So a valley line is a slope line to which many other slope lines converge going downwards, so into a channel. And a ridge line is the same thing going upwards. Now, the distinction between those two is that course and divide lines are topological features that affect the connectivity of the flow lines. And the valley lines and ridge lines are topographic features. Now, you can always see a topographic feature in the landscape. You can't always see a topological feature. And an important point to note is we're talking geomorphometry, not hydraulics here, and water doesn't always flow along slope lines, but that's the assumption that's made for this kind of analysis. Also, we kind of assume that small channels can be assumed to be well represented as lines with zero width, so we essentially allow slope lines to converge onto a single line. So I'm going to ask you to remember those tools, because I'm about to lead you into a new space where you're going to need them. So the first example is just a simple elliptical island with one peak in the middle of it, a very simple landscape. So the yellowy green lines there are contour lines going around the peak. The black lines are slope lines coming down off the peak to the coastline at zero elevation. Now, if we show that as a map in stream function elevation space, all the slope lines are vertical, running down, and the contour lines are horizontal. Now, the peak, which is that point in geographic space, has become a line in this space because all slope lines connect to the peak. So the peak has a range of stream function values, in fact, the same range as the coastline. It's also worth noting that the rectangles in stream function space don't map to the same size features in geographic space. So as we go down this slope, in this case, the areas, or the areas between constant elevation intervals and constant stream function intervals, they change. It gets more interesting when we add some more features. So this is just a similar shape thing, but with 2 peaks and 1 saddle. So now we have stream function slope lines with stream function values where not all the lines terminate at the same place. So the peaks now are represented as 2 separate lines on the stream function map. The lines that go up from the saddle, I beg your pardon, the lines that go up from the saddle in geographic space, they actually have different values of stream function on either side of the line. So these lines, the divide lines up from the saddle to the peaks, they are actually lines of discontinuity of stream function. So it has a different value on either side. Also worth noting is that the saddle appears in the stream function space twice, which is because it has these 2 different values of stream function. So that discontinuity in stream function value in the geographic space has a corresponding discontinuity essentially in XY position for the same value in same space in place in the stream function map. It's also worth noticing that, say for the 30-meter contour, that's a single loop in this space. The 60-meter contour is 2 separate loops. So again, we see the effect of these lines of discontinuity in stream function space causing breaking apart of the things in geographic space. And this is the same picture where we've actually added some ridges and valleys. So these are not topological features, these are topographic features. So we're seeing convergence and divergence of flow. So one of these valleys has been put on into the same place as a course line down from the saddle. In the stream function map, we can see that essentially we've got areas in the stream function map which map to just lines in geographic space. Another thing worth noting down here at the bottom of the plot, we have a valley line, but there's no course line associated with that. So valleys don't have to have saddles at their heads. And correspondingly, the divide lines and the ridge lines aren't the same parts of the landscape in this particular case. If we add a sink into this landscape, this is going back to the simpler one with just the 2 hills, we have a sink put into the landscape down here. That induces another saddle in the structure of the system. That's shown over in the stream function map as this saddle at low elevation. All the slope lines that descend to the saddle, that descend to the sink, stop at that point. They don't go on any further. So again, we have some divide lines coming up from the saddle. The interesting thing here is that though the divide lines don't have a discontinuity on them, but the course lines going down from the saddle to the sink and to the coast, they have a discontinuity in stream function value. So things do get a little bit complicated, but there are some pretty clear, consistent behaviours that emerge from all this. So here's an example showing the structure on a mostly real island. So this is an island that I identified as being simple enough to analyse and actually raised the coastline a little bit to eliminate some features that we're just going to confuse things. So this is a map showing we have several peaks. We have 4 peaks in this case. Peak 1 at this end of the island. There's peak 2, there's peak 3, and there's peak 4. Of course, they have each of them has a, sorry for flicking backwards and forwards. Each of them has a saddle between them, and various portions of this the landscape are represented as ridges and as valleys. So we have a branched ridge network here. So at the top, the northern end of the island here, we have 2 ridges that actually merge as they move up towards a peak. And that's shown in the stream function map as 2 areas that could be identified as ridges that become merged into one. And what's an interesting feature going on here is that one of these ridges, ridge 3, has both the concentration and a discontinuity in the same along the same line. So this ridge here, or in fact, if we look at this peak 2, it has a range of stream function values from 23 to 114, and also from 177 to 192, but doesn't include range of stream function values, which end up on these other peaks. We'll have another look at another real piece of landscape. This is a real catchment. I think I won't go into this very much, except to say that it's interesting to note that I think this is probably a general feature as you move to larger areas. Most of the stream function elevation map is occupied by valley features. So all of the convergence of flow down into drainage channels, of course, occupies much of the hydrological structure of the system. So that's all very good, but you may be wondering what the point of all this is. So there's a few questions that you can answer about the hydrological structure of a landscape that are difficult in normal space, but trivial in stream function space. And this is one. Given a short contour segment, an outlet of a catchment, and an arbitrary point in space, X, we can ask the question, is X inside the catchment or not? And once we have a stream function map, that answering that question comes down to just comparing a couple of numbers. So this is the point of representing topology with numbers. And note that you don't have to do any special processing on, you can choose any particular, any catchment outlet. You don't have to do any more than just calculate the stream function. You can answer the same question anywhere. You can extend that to asking about where a point is relative to a stream reach. Is it on the left side or the right side of the stream reach? So again, there are stream function values assigned to the slope lines coming up from either side of a stream reach, the bottom and the top. And for example, here, this point X, we know it's on the left side of the stream reach because its stream function value there is between B min and A min. If it was over here, it would have a stream function between B max and A max, and so on. One probably more important application is being able to derive a hydrological mesh based on from stream function and elevation. The key thing here is that elements bounded by flow lines, or slope lines, I should say, and contours are just rectangles in our stream function elevation space. So by progressively dividing a landscape into rectangles in this space, we automatically create a set of linked hydrological elements, which can be used for hydrological modelling. And there are a few mathematical aspects to this that I haven't really explored in a lot of detail yet. There's an analogy from a specific catchment area and specific dispersal area. We can talk about a specific stream tube area, which is at any point is just the sum of the upstream and downstream specific areas. And based on some work that Mike Hutchinson and I published a few years ago, we can show that the rate of change of that along the slope line, so going down the line, is just related to the planned curvature of the location. And the way this whole thing behaves suggests that there might be a connection with some sort of analytic complex function where we've got singularities and we have branch cuts and path-dependent integration around singularities. So again, that's not something I've explored in any detail yet. So brief conclusions. I'm suggesting this is a useful concept, both from a kind of conceptual point of view and numerically, and it has some useful applications in kind of answering some questions about hydrological connectivity in the landscape. And in my second talk, in a minute, I'll be talking a bit more about implementations. So I'm happy to take some questions at this point.
Yes, thank you very much. Are there any questions?
I have one.
Okay, Massi.
Okay, thank you. that's a lot to digest, actually, at least for me.
Yeah, sure.
I have a question. When you define topographic features and or topological features, is there a characteristic scale in your study area or in your approach when you create these flow elements? Or is there, or on the other hand, do you use any free parameter that you fixed somehow?
So I'm not assuming any particular scale here. It would depend on the kind of data source that you're analysing, I think. So I think someone made a comment looking at the paper going, in a a LiDAR DEM, which has quite a lot of fine structure in it, there's an awful lot of topological features, and I think that is certainly true. So I think for a practical analysis, you would want to use something that's suitably smoothed in order to capture the structure that you're actually interested in.
Okay.
Yeah.
So there is a scale. I mean, if you're interested in some structure, it has a well-defined size, let's say.
Yeah, I think that's true. So the theory doesn't impose any scale, but in terms of its actual practical use, you would, impose some sort of scale-based smoothing. Yeah.
Thank you very much.